this at home in your kitchen sink. You got your faucet. Remember we did this problem. Comes out in this stream. If you've got a kitchen plate here, what's going to happen is it's going to come out, hit the plate, because that plate's rigid, it's going to go out. And it's going to form like a really thin film here. And then like basically a couple inches away, it's going to suddenly look like that. Like from the top view, you're going to see like a circle. And you're going to see some wavy stuff. And then it's basically going to be a different height. That behavior is called a hydraulic jump because the velocity suddenly changes over a really, really thin distance. And you can actually analyze, so anytime, this is a pretty common theme through, as you saw from the homework, and in this problem, anytime fluid changes in velocity, changes in direction, you're going to be able to have losses associated with it. And that's just a consequence of satisfying consequence of satisfying linear momentum and mass at the same time. So, see if you can, at your seats, do this problem. Of course, this problem has gravity. You know, it's a river. This is a river scale one. This is a kitchen faucet scale one. But I would say start with the conservation of mass, then conservation of linear momentum, and then finally, those are all ingredients that you use to calculate the loss. Remember, loss is basically, there's three forms of the energy equation. Let's just review this. There's three forms of energy equation that you're going to use. The first form is the most general, which is not that usable because it's not one-dimensional. This is basically applying Reynolds transport theorem, which gives us, you know, how much things change the control volume, how much is fluxing across the control surface, plus the first law of thermodynamics, which tells us how much. The only way you can change energy in your system is by, adding work or heat. So that's version 1 that we gave. The second version looks a little different. What we did last time was we separated W naught in into two parts. One due to, well, let's see. Does anyone remember what are two different types of work that you can have? Shaft work, yep. And what about the other one? Yeah. Basically, kind of like pressure work. And so we separate those like so. You had plus Q over rho plus U squared over 2 plus GZ. Rho U dot add dA equal to Q dot net plus W dot shaft. Okay. So we've taken out the portion of W dot net that is pressure. Because of the sign convention, we consider positive pressure pushing the control volume outward. Work's only done if you have a negative, so that's why this is positive here. But the version I will be giving you in the quiz is the last version, where you basically consider m dot to be constant across all the control surfaces. That is, you only have one, basically, it's one-dimensional flow, and then you'll have the following. That's the version I'll give you on the quiz. That's what I gave last year. And so how do we get from that second line to here? You basically, you have 1D flow. And so you divide by m dot. rho g. Oh, so just g. It's already divided by rho. G. So physically, this equation, it should look very similar to back in quiz 3. That was like, actually a month ago, a whole month ago. We looked at the F equals ma along a streamline, and we got the following, that we said the sum of these three energies, just consider you multiply it all by rho g so that they have the same units, but it's equivalent. So we considered looking at F equals ma along a streamline, integrating that, and we showed that, hey, if you've got basically, this is what we did. We kind of like looked at, like this projectile fluid traveling up. And as it travels through space, three things can happen to it. It can go up in a gravitational field in which it'll lose energy. It'll change velocity, lose kinetic energy, or it'll change in pressure. And that's basically what this is saying. It's saying, well, the sum of the three energies, the pressure energies, the kinetic energies, and the gravitational energies, on the outlet should be equal when we have the inlet. But in life, there's usually some differences between those two, and those are called losses. So the difference between this Bernoulli equation, which doesn't have that, is assuming it's no viscosity all along the streamline. But the nice thing about this new equation is that you don't have to satisfy the viscosity assumption. You can have viscous losses. And that's why you have a negative sign here. And that's pretty important to note. There's a whole problem in the homework that goes about looking at, they give you a pipe. For example, imagine this is extended, this is a pipe. And they give you P in and P out. And they give you some angle. And they ask you, is the flow going up or down based on the pressures and the velocities? And the way to solve that is to recognize that if you have no pump in there, nothing giving shaft work, this should be 0. And the output energies are going to have to be lower than the input energies because you necessarily have losses. The losses are necessarily positive. So it's just like in life. You generally get out a little bit. Basically, the output here is always a little bit less than input. Just have some viscosity, some losses. And that's how you do that pipe problem in the homework. So remember, your input minus losses is going to be your output. So your output's a little bit less. And you want to consider this 1D. So just like the Bernoulli equation, you have to consider a streamline to apply this. So for this warm-up problem, where do you think you want to apply it? The middle of H, so we got a couple options. Let's just look at that real quick. And some people ask me about how to do all the quizzes. You do want to like try to talk these problems out, and it's okay to get them wrong. Okay, so we've got this energy equation, and there's a couple of places where we can apply it. We have one option is here between those two. The only issue is that they have to be along a streamline, and when you have this sudden expansion, you don't exactly really know where each of these lines are going to go. It's not totally obvious that the middle of this one's going to map to the middle of this one because it's changing in speed. Is there any other suggestions for where to put where we're going to use the energy equation? Yeah, that's another option. We put it here between these 2 points because if I've got a little rubber ducky here, it's going to end up at the surface unless someone shot it and it's like filling with water. But it's probably going to stay at the surface.
Are we considering these points outside
of
the
that's
pipe?
Chicken. Chicken's still good. Are we considering what?
Are we considering these points to be outside the pipe so their pressures are 0? Or
this problem, there's no pipe.
this is just free flow?
This is just like a river flowing across, and it's basically suddenly, when they go really fast, they don't slow down gradually. They kind of slow down abruptly. That's called the hydraulic jump.
Okay.
So this is air. this is water. This should be atmosphere. I mean, I suppose you could also choose a point down here, but the issue is you don't really know the pressure there. And later in quiz 7 we'll go over this thing called no slip. The things near the boundary are not actually supposed to move. So the safest bet is you also get a benefit from if you choose up here, you know what the pressure is. Okay. So maybe you can talk to the person next to you and see if you can. I'm gonna check up on you every couple minutes. See if you can do conservation of mass first, then conservation of linear momentum, and those will give you closed form solutions for basically the velocity 2. Actually, you don't even get U1 and U2. You just get H1 and H2. Let me go check this. Yeah, you're supposed to find the head loss just in terms of the height differences. Find the head loss.
For the area, would you just consider like a unit depth into the board, I guess?
Yeah, or you can call it a unit width.
Unit width,
Unit
or
of the board.
that's what I meant.
It's up to you. me see. Yeah. Pressure is correct, but it's not zero. Yeah. You know where it's from. But like, where does it arise from? What kind of pressure is it? Can you calculate the pressure exactly? Yeah, I think that's right. You gotta that integral. Remember, you actually don't have zero pressure on left and right. Does anyone know what those pressures arise from?
Would it be rho GH?
Yeah, gravitational pressure. So you got to do the integral.
So we're assuming these pressures are static, then the hydrostatic.
Yeah, you're assuming you're far enough away from these turbulent eddies that I've drawn that the pressure variation is simply hydrostatic. There's another point you should try to get the signs right, inlet and outlet. Remember, the left one, the n hat faces the left, the right one faces the right. In the end, we need to cancel out the u's. Yeah, I don't write the energy equation. If you have, oh, there it is. Yeah. Yeah, let's just start going through it. Yeah. All right. Okay. All right, so that you're going to have to use throughout. Okay. Remember, only your final answer is going to have H1 and H2. So you're going to have to eliminate. You need to eliminate. Eliminate U1 and U2. Remember, head loss is HL. And all these three equations, conservation of mass, linear momentum, and energy, they all involve similar variables. So we're going to have to eliminate some of these. So this is the version that you're going to use, right? Or this is the force, like I basically have a force applied on this control volume. Like literally, I've got somebody's finger just holding that control volume in place, making sure it's not moving. And this is one of those cases that, so we had problems in the homework that were like basically an iron pipe around something. Here, basically the only places that are non-zero, so you got P atmospheric equals 0 on the top, so no pressure on the top. We only really care about the horizontal momentum because only velocities are given, so we don't care about the pressure on the bottom. So what we do care about is these pressures. And we always call positive pressures going inward. And you better bet those are positive pressures because it's all underwater. It's all due to gravity. You know, divers experience all this. Divers go underwater, they experience positive pressure even when the water is flowing. All right, so the left-hand side, this should be quite easy for you by now, doing this left-hand side. If you have some difficulty, make sure this is probably one of the last times I'm going to go through it before the final. Make sure you do get it. So here you've got a velocity going to the left. Here you got velocity going to the, both velocities are going to the right, but the normal vectors are pointing in the opposite directions. So you got U1 x hat times negative U1 plus U2 x hat times positive U2. I've got the areas. Here the areas would be H1 times, I called it W, plus U2 x hat positive U2, H2W. Remember, they have different heights, H1 and H2, and that's equal to the sum of the forces. Okay, so let's just do negative U1 squared H1W plus U2 squared H2W equal to the sum of the forces. Okay, so you should have that. That's pretty much a review of quiz 4. Any questions on where these signs come from and how to calculate this integral? Yeah. Yeah, thanks. Bro, thanks. All right. But if you're going to take the final, you've absolutely critically got to know how to do that integral. You'll see it in 2 problems on the final. All right, now to review how to do the hydrostatic pressures, right? You got these pressure on 2 sides, and you don't even, for hydrostatic pressure, you don't even need to care if the fluid's moving or not. You just know that's one H1 and H2. So we'll do this P1A1 is going to be integral of P dA. And we do that between z equals 0, z is equal to H1, equals 0, z equals to H1 of rho g z w dz. This is the pressure, and this is that's the dA, right? And that gives us rho g w squared over 2 and H1 squared. And maybe some of you remember that from before. All right, so basically, and P2A2, and this is going to be in the positive x hat direction, P2A2 is going to be in the opposite direction, rho GW over 2 H2 squared x hat. Pointing the other way, right? Of course, if they're the same level, then basically hydrostatic pressures will balance. Okay. So we put that together.
Doctor Who?
Yeah.
How do you know when you have to apply the hydrostatic, like do that calculation as opposed to just P times A or?
Well,
I guess how do you know when hydrostatic applies?
well, here it's like I kind of drew it with like a rubber ducky. Physically, it's a big enough scale that gravity is there, and I also drew the gravity vector. It's basically a non-negligible force in this system.
So we're just saying it's a very deep thing of water, like H1 and H2 are big.
Well, yeah, even to be honest, in your kitchen sink, if you do this, this calculation still involves gravity. That's basically, like, for example, if you didn't really have gravity, you wouldn't be able to have these, the difference in gravitational pressure on each side is what's holding this control volume in place. It's what makes this a static problem. Otherwise, this thing would be kind of like a wave. It would just keep on going from left to right. The only thing that's sort of keeping it in, like this is stationary. Even though the velocities are going, that jump is in a constant location. Like if you do this on your kitchen sink, this is like, literally like, I think, 2 inches. It's stationary, and the only way it can stay stationary is if you have 2 forces on the right-hand side. I mean, if you were to just say P1A1 and P2A2, you wouldn't be able to continue the problem, because the final answer is supposed to be in terms of just H1 and H2. So this tells you that basically the amount of energy you lose isn't a function of how fast you're flowing. It's only a function of basically the differences in heights. Particularly the bigger difference in height, the more losses you're going to get.
Got it.
And in the quizzes, I'll try to use gravity, I think. All right.
So it's basically when gravity's involved is when hydrostatic applies.
Well,
okay.
Yeah, or when you have some really large amount. Well, you're right. It doesn't have to be large. Camera 2. All right. So we put this together. You get. We can also get rid of the rows now because we have what rows on both sides. U1H squared H1, and we'll get rid of the W's because we don't need it. H2 is equal to G over 2 H. G over 2 H1 squared minus H2 squared. All right. All right. So that's what we have so far. Now, the rest is actually just some algebra. So from conservation of mass, we can eliminate one of these things. So you can say U2 is equal to U2 is equal to U1 H1 over H2. Okay, and then if you substitute that in here, you're going to get an expression. You'll get basically U1 is equal to a function of G comma H1 comma H2. Okay. Right, you can see you get U1 on the left and everything else on the right. And you're going to get this. And the energy equation states that P we'll use the P1 over rho G plus U1 squared over 2G plus Z1 is equal to P2 over rho G plus U2 squared over 2G plus Z2 plus HS minus HL. Okay. All right. So the progress we've made so far is we've got an equation of just the first velocity. Or you can only get the second velocity. It doesn't really matter. You can always convert between the two. Simply as a function of the h's and g's. Okay. Now, this last step is because we're basically trying to solve for this HL, right? So there's no turbine here. Here, Z1, we know exactly. So we're going to use, if we use a point where the rubber ducky is, this is going to be H1, this is going to be H2, substitute for those. It's a free surface. Just like a free jet, there's a pressure of 0 above you, and then the only way you can have equilibrium is if that pressure is 0. So that's 0, and that's 0. All right. And so you have this, U1 squared plus U2 squared over 2G is equal to U1 squared minus U2 squared. Let's do 2 minus 1. Then we get a negative positive HL. U2 squared minus U1 squared is equal to HL. All right. So that's what the energy equation gives you. And what you're going to do is substitute for this there for U1 and for U2. And after some algebra, you'll get this. All right. So that says if physically, if the heights don't change, if H1 is equal to H2, there should be no losses. And that works because the velocities on the left will equal the velocities on the right. There shouldn't be any losses. But as soon as you make H2 a little bit higher than H1, the losses increase dramatically to the cube, to the cube. Yeah.
What happened to the H2?
Oh, yeah. Sorry, I forgot those. All right. Plus H2 minus H1 equals H1. Thanks. And so the original energy equation said this, and this says the losses is equal basically the differences in kinetic energy between the beginning and end, and the differences between the gravitational energy between the beginning and end. And then we're going to use the boundary equation substitute for U1 and eliminate it. Okay. And if you want to see the full algebra, I think I uploaded this problem to the website, but if not, you can come after class. Okay. All right. So physically, does everyone understand this problem? Kind of. The losses are basically just going to try to calculate basically something that's you're not getting the losses, and you just want to calculate what it is. Okay.
In that first integral of P1A1, why did you write the pressure was negative?
That's the definition of whenever we do the force on a body, we write negative pressure. You just want to make sure your final thing is positive.
But how would that come out positive if you have a negative?
There's an n hat. There's an n hat there too.
Oh.
So it would be from the direction of n hat. Because we always call n hat to be outward normal, but the pressure actually goes into the body. Okay, so on Friday, somebody said they had some questions on homework. Do you guys want to, if you guys have attempted the homework, do you guys want to talk about which ones that you want me to sort of go over?
Yeah.
All right. Any takers on the sprinkler problem? You'll definitely need to know how to do the sprinkler problem. Variants of it have been on every quiz for the last many years. You guys know how to do, so the sprinkler problem, there are 3 parts. Review very briefly. 5.83. All right, there are basically three parts. Force to keep it stationary. It's actually all torques. This is a sprinkler. And for this one, you need to use R cross U for the sum of the torques, where this is M dot. All right, and that's over across all the entire control surface. So, if there's two heads, this is going to be, if you have an M dot here, this is going to be M dot over 2, etc. Right? And you multiply by the number of heads. But there's basically three questions that can be asked. One is the torque to keep it stationary. Given Q, the flow rate into the sprinkler. Then it's the torque to keep it at constant speed, constant angular velocity, omega, and the omega such that no torque. I think everyone should be able to do part A without too much difficulty. That just requires you to, calculate this R cross U correctly and use the M dot. Part B, you should make sure you practice that at least once or twice. You necessarily have to use W equals U minus UCV. You have to use this definition of relative velocity. Okay. Where basically, remember this thing is, okay, this one it's going to rotate like this. Basically, if you're like a little ant on this thing, you're going to see basically from this part B, you know W, so you know this. You know this. You're going to be calculating U. For example, UCV is going to be something like R times omega. W is going to be given by your Q. That's the speed that stuff's leaving the sprinkler, because that hasn't changed. Once your thing's rotating, whatever comes in's got to go out. And the difference between those two will tell you what the actual velocity of that fluid is in the stationary frame. So you have to do that. You have to use that for part B, because the equation for part B is a little bit different. R cross U rho W dot at dA equal the sum of the torques. Okay. And I'll give you that version on the quiz. And part C is quite easy. It's basically just considering if you want to have 0 on this right-hand side, what is the omega such that you get 0? But you should definitely practice using this relative velocity. So I kind of sketched out the big picture, because I think we went over this. We did a whole hour on this in lecture a few days ago. But is this okay? Yeah.
Can you go over how the angles work into that? That was the part of the problem that I had a hard time with, because I thought that the cross product would create like a cosine or sine, but it didn't in the solution.
You're talking about for 5.83?
Yes.
Okay. All right. So let's draw this a little bit closer to the actual problem. Actually, let's just do this on the next board. 4. All right. So this particular problem, you have fluid it looks like it's to the horizontal, right? Right, so, yeah, it looks like it's going upward. All right, so you got 3 heads. Right, and if I draw a top view, basically they'd be kind of going. And they said the actual vector is, this is actually theta, and this is to horizontal. Okay. So the ideal sprinkler, they'd be all spinning, and you would have theta be 0. But this one looks like, for some reason, it got bent or something like that. Or I guess maybe you want to have the water being going as far as possible, so you have theta to be non-zero, so you have it going up. Okay. So that's going to change not your m dot, but it'll change the amount of momentum that each thing has. So we got r cross u rho u dot n hat dA is equal to the sum of the torques. Okay. Now this part is still m dot. But r cross u, here we're going to have, so here u is going to be u. Well, the component that is actually in the vertical direction, we can get r u. So we, in this notation, we had capital R kind of u cosine theta. So when theta is 0, you basically get the full component of r cross u. When theta is non-zero, you get you don't get that component. And that's times so that's times n. That's we keep it general, and this is m dot over n. Okay. So in this case, we have n equals to 3. M dot was simply rho times q, and u is q over 3 times the areas, whatever the area was. Pi. What did they say? They just give it to the null, like I said, so that's enough. So you basically just substitute that. So this thing is r cross u. And you can also have a z hat. So what this has done is basically only take the component that's basically in the direction of motion. There is, you can imagine there is another torque that's applied by a force in that direction that's causing it to like kind of splay, but I think that cancels out in all the directions. So you only consider the r cross u in the z direction. This is r cross u component in the z direction. The z hat direction. Does that help?
Yeah.
Okay. Yeah.
So I have two questions. One is just a general one. So for when we're doing relative velocity for UCV, we can always say it's r omega.
Yeah. Okay. So I actually still have it up here. So here, unfortunately, the way I drew it on the first board is the opposite of the way it's going on the second board. So if we actually do it like the problem is going, it's going to be traveling this way. That's actually positive. So that UCV, in that case, UCV is going to be to r times omega times theta hat. Yeah, that's a velocity.
Okay. And would you mind going over the angular momentum problem in the last year's quiz?
Let's do the I guess we could do that. We could do let's do all the homework first, because I think everyone definitely tried that, and then we'll go to this at the end. But that one is also very, very similar to this one. The only difference is there's one outlet.
Before you change problems, I just had another question about this. Was it they incorporated the relative velocity as well? Um, do you basically just plug in um, for instead of u, do you just plug in w plus ucv into the r
That's exactly
times
right.
u?
So, um,
I was
all right,
just
so
confused what they did.
for part B, um, oh, in this,
They somehow said the relative velocity was equal to ucv only. Or sorry, u.
what they're supposed to do is, so you're supposed to write this minus UCV. And like we said, this is R omega theta dot, theta hat. And this one is basically, if you're going to have U times, the fluid is actually going in the negative theta hat direction. So you're going to solve for U. U is equal to R omega minus U plus U minus R omega. R omega minus U theta hat. So you should be substituting this into your R cross U. So this part should stay the same. That should still be m dot. But this has now become R omega minus U. And R cross that is just going to be capital R in front. And it's going to be Z hat. Okay. They should be doing this. Do they actually do that?
How could you say that w is equal to negative u? Because I thought.
Okay, this is a really important point. All right, so Daniel asked, how do you know what W is when it's spinning? This is the whole point about this second part of the problem, in that in the previous problem, the whole thing was stationary. So U was equal to W. So for part A, U is equal to W because there's basically UCV is equal to 0. Right, now in part B, the thing is you're letting it go. So once you're letting it go, all you know is the relative velocity. Like I said, if you're like an ant here, your life has remained the same. Basically, because the fluid coming out is still the same. So W is what we have as before. But the velocity in a stationary frame is what you have to calculate. And that depends on how quickly that frame is moving. So you've got to have this. So basically, this has stayed the same because whatever goes in has to come out. It looks like they're doing the same thing, maybe up to a sign. It looks fine to me. Which one was last year's torque one? Which one of these was it? Can you recognize it? This one? All right, let's talk about this real quick. All right, since we're already on angular momentum, let's talk about this one from last year, which is actually not too hard a problem compared to this one. So this is the uploaded quiz 1, quiz 5, number 1. All right. 2019 quiz 5, number 1. All right. How's this doing? So we got this thing that's kind of on an axis. Theta. So fluid's coming in. That thing has some big diameter, and it narrows the small diameter. Stuff's leaving. So it goes from capital D to little d, and it's got an axis. So that has a length there, L, and this whole thing is spinning this way. This whole thing is spinning. So you imagine, this is kind of like if you have a garden hose or one of those fire hoses and no one's like holding the end. You got this instability, it's going to start spinning. And so you're given Q, D, D, omega, theta, find the torque to basically drive the device. Because like I said, fluid doesn't want to spin, doesn't want to go in all those directions. It just wanted to go straight. By forcing it to go in all those directions, you're going to generate some fluid torque. Yeah. Why don't you see if you can think about it at your seats for a minute before I give it to you. And so we're going to use the same equation as before. Right.
The reason why I asked about this problem is because it was done differently than the way we've been doing it this year. The second part wasn't treated as m dot. You plugged in the U underline and W underlined. So you have to find W.
Yeah.
And then also your UCB, and then both of them are plugged in.
Yeah. W is just given by Q, right?
So I do it the way we've been doing it this year, but it's different. Like the answer I got is different. I'm not sure if it's equivalent to this. This is the R.
Mm-hmm.
This is U using the relative velocity. That's EV. And then you have m dot, which is rho. U is given. I'm not sure if this would be like right since it's like a very very different from the actual solution.
I think you don't have that, right? You just have
Yeah,
that.
yeah, the solution doesn't have that. Yeah. Needs to cancel it out when you plug it in for W.
They don't even talk about it, right?
Do you see how they
Yeah.
cancel it there?
Yeah.
Yeah. Like the way we've been doing it this year, it would give a different answer.
You want to draw it on the board? Show how you did it?
Sure.
Yeah, you can explain it how you did it.
So we're given Q would be equal to omega and theta. So so the way they did it in this problem is like different than the way we've been
Yeah,
doing
just
it.
do it the way you think we should do it.
Oh, okay. So the first thing you would do is, well, this is M dot. This is M dot. And you want to find U underline using the given relative velocity and the velocity of the control volume. The velocity of the control volume would be U equals R omega. And R in this case would be L. And you want the vertical, I guess not vertical, but you're looking at it, you don't care about the horizontal, so omega would be going this side, and then omega would be for your underline. So then if you're looking at it, this portion, you would need the sign. The sign term is vertical.
Mm-hmm.
So it'd be L sine of theta for this omega. So omega equals sorry, U equals R L. Or
R is equal to L.
Yeah,
L sine.
R is equal to
L sine.
L sine of theta.
Yeah.
Omega L sine of theta.
Mm-hmm.
And then you also have this W from the flow. So Q equals U times A. But in this case, U is W, the line. And the area, so you only care for the area, you only care about the fluid that's leaving. So that area would be with the small diameter. And the U is given by, or you want to find this U, which is W. So you can do U equals U over A, and you're giving Q, and you know the area given the small diameter, so it would be U over pi d squared 4, and you can rearrange this to 4Q over pi squared. So now you have.
But that's in a certain direction, right?
Yeah. So if you're saying counterclockwise is positive, then this term would be negative. This would be positive. Yeah. So now you have R and you have this also. This is M dot, so this you can just write as rho Q. So the way I did it was R, the radius would also be L sine of theta, because you're only looking at this region to see the torque that would be moving, and this would be L sine of theta. And you know this now because you know this. This is UCB. And you know this, so you can say 4Q omega L sine theta rho Q just M dot. That would equal the torque. But this is different than how we.
Yeah, this needs to be corrected, and I'll send. It might, maybe it boils down to the same thing, but I have to check it. But yeah.
But would this be correct the way I did it or no?
The only difference I would say, let's just do a second board. The only thing I would say is that I would define our coordinate frames. So, you can sit down. Thanks. All right. So. We might as well just have the whole thing. So basically, it's going like this, and we might as well just. Okay, so we'll call that Z hat, and then basically the R hat. So R cross Z. So the only thing I would clean up a little bit would be that. So we have U is equal to W plus UCV. UCV, I would just put equals to this is the effective radius of that thing, like Vishwa said, and I would just have call that and this is the theta hat direction.
How do you get the velocity term? Where's the L coming in that term? I mean, you've got a velocity term, which is UCB,
Yeah.
and now you're changing it into WL sine theta, which is
This is omega.
Omega, but omega L sine theta, which is an R cross U term.
L sine theta is just the effective radius. So,
But you still have a radius term when you should be working in velocities. You've got an extra radius term, and I don't know where that extra length is coming in, and the units aren't messing up.
Professor, can you move the board or the camera?
Yeah. So just like the other sprinkler problem, you basically have this is the velocity of something that's spinning in a circle like this. If you've got the omega, basically you have L sine theta as the radius of this thing. So the velocity, and this is omega in radians.
Okay. I thought omega was in actual distance.
It's not super, because there's omega and there's W, and they're different. Yeah. So this is omega in radians per second. So you basically got, you have that, and the issue is that Q, you've got some so W actually has some components in the Z direction and some component in the R direction. So to be really precise, we would write as W is equal to, so it was called, we're given Q, all right. So we know this, 4Q over pi d squared, right? That's just the flow rate divided by the area of the thing. Okay. But W actually has two directions, as a Z hat direction and an R hat direction. This was called theta. That's R hat. So we got. Those units. All right, so when theta is 0, it's all in the z hat direction, and you don't get any kind of torque. When theta is equal to 90, that's bad because you get lots of torque. So that's the only way I would change that a little bit. And then but then again, we add these two up, and you keep on going like before.
So are we assuming the relative velocity is perpendicular to the control surface? And then I guess UCV is tangent to the circle that the whole thing's rotating about? Like if you were to actually like draw out the vectors on the diagram.
Oh, for W? Yeah, it would kind of look like you basically it would be like this. So you have this is the relative velocity leaving. And you got some component going to the right and some component going in the radial direction.
And UCV would be like tangent to like the I guess the curve, right?
Yeah, UCV would be going into the page. So UCV would be like going in because the whole thing is spinning. Oh, and here's the part that I think that why the solution is right, because these are so that's and then so U is equal to the sum of those two. So if we add that all together, we basically got a z hat and an r hat and a theta hat. The thing is that the torque is r cross u, right? And the r is in the r hat direction. So the one that we actually care about is just this theta hat component, right? So basically, these basically are going away, and you only care about this component. Right? Because r and r hat doesn't give you a direction. Z hat cross r hat gives you some weird torque that basically you've got to have. This thing's got to be anchored so it's strong, so you can resist that torque. The only part that sort of keeps on propagating through is this omega L sine theta, and that's multiplied by that thing. So that's why the solutions are still okay.
So that wouldn't be right, I guess.
So what was the issue with here is that this W, you got to keep in mind the direction of W. Okay. Here, you're kind of assuming it's like the Springer plum in that W is going perfectly normal to UCV. Okay. Like that. So if I were to add in red what's missing here, we need a theta hat here. And then here you kind of assume that it was I don't remember what the other problem was. I think you kind of assumed that was R. So R cross theta would give you that. So you assume that basically these are, but actually this R hat is actually Z hat plus R hat. Yeah. And the other one's actually in theta hat. So that's the tricky part of this one.
Why is UCV negative theta hat? Oh, my audio coming.
In this one?
Or yeah. It was because won't W be? I figured W would be going counterclockwise, which would be positive.
It's going this way.
Yeah. Which would be in the direction of positive Z hat, right?
UCV is this like basically you're kind of tracking this thing and it's rotating in this theta hat direction.
Yeah. So I was just wondering why it's got a negative.
Here I have a positive.
Okay. Yeah. Sorry, it's negative over on the left on board 1.
Oh, okay. No, it should be this.
Okay.
Okay. Let's see. All right. That's time. But now we got office hours commencing. I think other people had issues on the homework. So, does anyone ask about any other questions on this homework? Yeah, and you guys can leave. Class is over. But I'll just I'll just hold office hours here. Do you want to
Doctor,
shout it out?
I need to.
Okay.
I have a question about that.
Yeah. Oh, okay. So let me just address the board so people are actually here. So we got this question on 5.128, two jets colliding, and the key thing is there's two jets. So there's no pipe. There's no external pipe on the outside. There are problems in the book that there is external pipe, and there you have to consider pressure. But if there's two external jets, P is equal to 0 everywhere.
Okay, so unlike, we had almost the exact same problem last year, but it didn't, it looked the exact same, and we didn't assume there were just 3 jets, pressure equals 0. So what's the indicator?
Last year?
Last unit, 2 years ago. When we considered that, how we did the problem?
Was it the problem with the plate?
No, it was this is a repeat problem, and it just was changed up a little bit.
I think the previous problem must have been in a pipe. That you have two, that you have basically you have some rigid pipe. Definitely there's some problems with if you have a rigid pipe on the outside, then you can have non-zero pressures. And P is not. But when it's basically free jets, then the pressure is 0 everywhere.
So it's just simply a factor of that.
If you have a pipe or not. Yeah, the external pipe allows you to maintain non-zero pressures. If you don't have that external pipe, the fluid just kind of oozes and it does what it wants. Yeah, since you're here, go ahead.
So I don't know if Blake is still on, but Blake and I put together a prototype yesterday, or this past weekend, and so we're the hot wheels team.
Yeah.
Basically, we figured out a couple things. One, that a hairdryer is not substantial enough to, so we have the lightest.
Yeah, Blake's there.
Okay, thank you. So on Onyx Master, we have the spring with the lowest coefficient. So stretch easy to get.
Oh, it's still not. I think it says that Hot Wheels car has a really small surface area.
Exactly. So you had mentioned last week about testing the different cars.
Maybe you could do a 3D printed shell or a paper shell to make that.
So what we're thinking, would you be okay with us taking the car and making different surface areas? Because we found when we added an index part and used a shock vac, that's how we got the best result visually.
Oh, okay. But the what's it called? The hair dryer is still not enough.
Hair dryer, we get a little bit of difference with the area, change in area.
Yeah.
Shock vac is big.
How big is your cross section of your window?
Right now it's 4 inches in diameter because we have to have space for the car and the water area.
Is it possible to make that smaller so it just encapsulates the car? I know that's going to change some of the things, but then you wouldn't have to use a shop vac. You would still use the hair dryer.
The problem with that is you got the track to keep the Hot Wheels
Oh, you already made that.
straight. Well, I mean, it's
really a factor of everything that goes inside the Hot Wheels car is
Oh, so it's already basically 4 inches. You think it's small? You can make it.
Yeah.
Okay. So you're going to add some index cards to change the profile of the car.
Yeah.
Yeah, that's fine.
And the area is easier to see because then we have
So you can just add one index card and make it change the size or something like that?
Yes. We can do an index card and index card for 2, 3.
Yeah, you could do index card and circle or something like that. And I mean, the Hot Wheels car, we were originally thinking that the streamlined shape you would do to tell, but the problem is it's too small.
It's way too small.
There's some well-known drag coefficients of maybe you could suspend something above the Hot Wheels car, just be like the track, and you can basically suspend some objects. Like, for example, I know the drag coefficient of a plate going this way is a lot less than the plate this way. You can compare those two maybe. So this one would be really easy. You have a car here and it's like holding it. This one you'd have to have like a little toothpick and holding it or something like that. Something. Yeah. don't want to lift though, because the car's going to go flying. But maybe some
Doctor Who.
drag coefficients. Hold on for a second. I'm almost done. Maybe compare like 2 or 3 things that people would find kind of surprising for drag coefficient. Yeah.
And then one thing we noticed was, as you go along the track,
Yeah.
The velocity you get from your air drag or
The shot back.
decreases.
Yeah.
So what we were thinking is that we can take increments of like a half inch or so.
Oh, it does decrease. We haven't talked about that yet, but that's due to something called entrance length. You put laminerizers in the wind tunnel? Oh, okay. But the velocity should decrease as you go down in length.
Yes.
And that's what happens?
Yes. So
Okay. That's due to losses.
we're focusing on, classic out.
Yeah.
So one thing we're
When you have a minute, could I discuss my course project with you?
Yeah. Give us another like 2 minutes.
But we were going to take we have an anemometer and an air dryer, and we're
Yeah.
going to take half-inch increments and get like what it would be from the.
Oh, because the fact is that I see what you're saying. Basically, when you have the spring, you're assuming that whatever length it's stretched to, it has the same velocity.
Yeah.
But it actually decreases velocity, so you have to calibrate it in some weird way.
Calibrate the velocity based
How much does it decrease?
quite a bit. So like when we were playing with the velocity, we didn't see it when we changed it or when we doubled the
Yeah.
area.
How long is the holding the setups this long?
So about 2 seconds.
Yeah.
Shoutbacks sometimes work better in suction than in flow.
Yeah. We were decreasing probably about 5 miles an hour, about every
Okay.
8 to 10 inches.
Yeah, I think if you kind of tell people, I guess the easiest way is just calibrate it. I think that's already pretty interesting for the audience to know that it decreases. I'm surprised the losses is that much.
Well, we didn't really have, we still don't have it too. But that's just what we found out.
Okay. Oh, once you have the tube, it might be different.
Yeah, and part of the problem is, with the spring, we're starting already some extreme, I say, no, but some distance already away from the shop back before we even experience that.
Once you actually you don't have the outer tube, that's going to change everything.
Yeah, well, so we don't have the tube because Amazon is mean, but.
Because once you have the tube, I don't think you're going to have that much of a loss.
So, no, we were building, structures. And,
We basically wrapped some like paper around the track. Like we basically used like a cardboard tube. And now, granted, it was larger, so the diameter was probably like 6 inches, but it didn't really change anything. So I mean, maybe smaller would help, but.
Okay.
But we should be able to work with a plastic tube as this next week.
Okay. I'd be interested to see how much losses change with the plastic tube. You got to do Steve, your thing planner, but you're already learning a lot of things already. I think about loss. I think it sounds fine. And if you calibrate that sounds fine too. The shop vacs is slightly less convenient, but I guess that's just the way it is.
Yeah, it's definitely less convenient, but.
Unless you totally don't use Hot Wheels cars and use like styrofoam cars, but you have to manufacture the wheels. I don't know this. So I think stick with shop vac. I think that's fine.
At least we know that all those cars roll. That's the starting point.
Yeah.
Oh, no.
Okay. I want to write down this.
Doctor Who.
Oh yeah, Jaden, you're at first dibs, right?
Yeah, but I can't.
I got your quiz with me here.
Yeah, I can't meet at 9:15. Can I meet at 12?
Oh, you have class now?
Yeah, I have a meeting. Can I meet via Blue Jeans at 12?
But we're gonna have the same issue is that I have your quizzes. You gotta pick up your quizzes probably.
Okay. Because I have my quiz 1 and 2. Is it possible to go over all 4 of them today?
If you have them, if you can come get them. The earliest you can come is 12.
Yeah. During like your next office hours.
Okay. let me write you down then. But how are you gonna pick up your quizzes?
I can come at 12.
I don't know if I'll be here at 12. Let me see if I. Hold on. You have a meeting from now till 12?
I have one meeting from like 9:45 to like 11, and then from 11 to 12.
I'm still lost.
You just go first, man.
Okay. Yeah,
Is
so
it possible to like leave it with somebody, like in somebody else's office or something?
Maybe I'll leave the whole pile outside. No, we'll figure it out at 12.
Okay. Or do you have like a mailbox on your door that you can leave it in?
The problem is there's like a huge number of quizzes, so it's easier if you just come to class and pick them up. So,
Okay.
we'll figure it out. Just go do your stuff. We'll figure it out at 12.
Okay. Like you can't leave like just my 2 quizzes in the door?
I'd have to sort them.
Oh, okay. Yeah,
I
it's
did.
just my quiz 3 and quiz 4.
Yeah. I'll try to be here at 12, and we'll try to have a quick meeting.
Okay.
Yeah. All right.
Thank you.
Yeah.
Doctor Who.
Yeah. What's up?
Yeah. I was trying to meet with you on Friday.
Oh
just
yeah.
to
Sorry about
discuss-
that. Do you have a question now? Can you ask it now?
Yeah. So I kind of like, well, during our last meeting, you were when you were talking about the olive oil and water or whatever, and then I mentioned I thought maybe like centrifugal force came into play to cause the mixing.
Yeah.
So like I thought maybe you can make the argument that the centrifugal force played a role in the mixing fluid because since it's inversely related to the radius of curvature, basically as the radius increases, so as the bowl gets larger, that force basically goes to 0. And so I thought that force, when it would hit the bowl's wall, that would cause like an equal and opposite rebound force back into the fluid. And as your radius goes to 0, that force would go to 0, so your rebound force would go to 0. So I thought, as an explanation for what we're seeing, like the bigger bowls have lesser rebound force, which would cause like no disruption.
It seems like it could be plausible, but you got to get some experimental evidence. Maybe get a really transparent bowl from the side view and see if you can put little particles or something like that, so you can see like basically you kind of have this idea of what the streamlines look like, and I'm not sure if that's actually the case.
Right. That's what I was thinking. Maybe like putting sparkles or something in clear water or whatever.
Yeah.
Because like I thought
you don't even need to use egg yolk for that. You just need to use like I'll just get some pepper or something like that, or I don't know, some noodle chunks or something like that, and try to view it from the side. But if you can take a picture and the explanation you have, you can summarize in 2 or 3 equations, then yes, it's possible you can put in your presentation. But if it's something really long-winded and you don't have evidence, the class is not going to be.
Well, my thing is, so like I thought with the smaller bowls, like that rebound force would create some sort of like turbulent flow near the edges around the bowl or mixing apparatus, and I thought that was what increased mixing in a smaller bowl versus a larger one, just due to that like turbulent flow on the perimeter. So basically,
I calculate the Reynolds number if you really want to say there's some eddies. So maybe calculate the Reynolds number. I kind of don't. It's hard for me to see visually what you're talking about Any way you could share screens and like draw a picture or something?
Sure. I mean,
Or we'll be here for the next at least 30 minutes or so. You can try to get your
here.
technology ready. Explain.
There's this website I can like draw stuff with.
Yeah, it's called Miro.com, I think.
Oh, I was using like Sketch.io.
Yeah, that works too. But if you send me the link on chat, then you can draw it out. And I'll let the people here ask while you figure that technology out. Go ahead.
Do you want me to share my screen then?
Okay. Why don't you see if you can, if you can, or you can share screens, and then I'm going to start answering some questions here because these guys have been waiting.
Okay.
All right, go ahead with the homework.
Okay, so for that same problem, 5.128.
Yeah.
So the second part of the problem, so the first part just asks to apply the linear momentum and get the velocity, and so that was like the velocity and the theta, which was not bad, but then the second part, it asks you to determine the loss. But they did it a different way than we've been doing in class, so I wasn't sure if we'd be expected to know how to do it that way for the quiz. Because they used their previous equations that were relevant.
The reason why they can't use the 1D equation because it's got two outlets.
Okay.
It's got two entrances and one outlet.
Yeah.
The other one's like a 1D equation. It's kind of assuming it's really 1D, but this is really a 2D problem.
Okay.
So that's why you can't use the one from class. Like if it were something like this, you could definitely use it.
Yeah.
Because basically, what goes in and out.
That's what I thought.
But here, the issue is that basically you have basically 1, 2, 3.
Mm-hmm.
Oh, my handwriting's really bad. So you basically have to track. The nice thing is you don't have any shaft stuff. So basically you add up the kinetic energy and U-hat, I don't think they said there's any differences, right?
No, they just put the U-hats on one side and just said that's the loss.
Yeah.
Like they just said that those variables represent the loss.
Oh, yeah. Okay. So it's basically like they put everything. Basically, well, the difference between basically the kinetic energy of these is going to be your losses. If you got less kinetic energy and then you start working, you have a loss.
Okay. But for the quiz, it would just be 1D.
I would say anything like homework is fair game too.
Okay. Because I don't know, we just haven't really worked with the other equations. Just the one you've given us.
You're right. We haven't done much examples on this, but it is assigned for homework. You're right. We didn't do it in class.
Okay. And then I just had a few smaller questions on some previous problems. So
yeah. Ark, are you okay on that one?
Yeah.
5.128. Okay.
Okay. So.
Oh, and thanks for doing that one on the board for the class.
I did it wrong, but that's.
No, the class needs to see various ways to do it.
I understand it now though,
It's really subtle. You basically have to
really subtle, yeah.
a vector.
And it wasn't on the solution.
I did not explain it in a full manner.
Yeah. But I understand it now, so. So in 5.125.
Yeah.
They wrote a note about how. So I got it up to equation 2. If you look at the solution, so I got it up to there, but then equation 3 they changed the area from A1 to A2.
Yeah. Okay. Let me draw this out.
I wouldn't have known to do that.
Also, I was wondering, for these types of questions that are in class and for 5.125, have we seen like a pressure by a force type of, have we seen that before in other types of problems? Where the pressure times area of the force?
No, yeah.
Yeah, that's what we did for the hydraulic jump thing.
We've seen those, but I'm just asking about the point.
Okay, so this problem. Why does Georgia Tech get rid of all trash cans?
I don't know. There's one outside. There should be one in here.
All right. And let's just erase the board. I gotta erase. Okay, yeah, this that I wouldn't expect you to know to do that. They did that based on experimental results,
Okay.
and they told you. But that's why I signed up for homework. if I were to give that in a quiz problem, I would sort of tell you that you got to assume P1 over that thing.
Gotcha.
All right. All right, so sudden expansion. All right, so in reality, so you have fluid coming in and basically it's leaving uniformly out. In reality, there's these eddies that preserve the initial P1, U1 that basically have the same pressure P1.
Okay.
That's basically what they're assuming.
Okay.
But you wouldn't really know that unless and they only figured that out experimentally. Apparently, if you don't use that, you actually get the wrong answer. So you won't have to. You need to know that. I'll tell you that you have to apply P1 to both.
Okay.
Yeah.
And then just these are more relevant questions for the quiz. So for the previous problems without the shaft work, so let's see, they're 5.100 and 5.102. They manipulate the equation and multiply both. So if you look at 5.102, so basically what they do is they manipulate the original equation and multiply by g.
That previous one we did, that was 5.
Yeah, that was the one from the homework also. That was
5.125.
123. Oh, that's 125. The one we did in class was 123.
And you went to 102, right?
But that one is 105. Well, I mean 125.
So 125.
The in-class problem was 123.
All right. And which one do you want to talk about now?
That one.
102.
Yeah.
Yeah. What about it?
So these problems, they manipulate g and multiply both sides by g so that the pressure term and the velocity term don't have g anymore, so it's just gz. So when they do that, would you get g times the loss, like gh sub l? Because that's what they're doing, right? Like wouldn't the loss term be different now?
Yeah, the loss will have different units.
Yeah. So g h sub l would now be the loss.
Yeah. So yeah. Why would they want to use that new form of the equation?
Yeah, the book always uses some like way different units and terms that we use. Kind of throws me off when I'm doing the homework.
Yeah, because when you're doing the problem solving, like setting up is mostly good.
Yeah.
Problem solving is kind of.
But
if you don't multiply by g, you get the wrong answer. And that's what I initially did, and I was like, why is this wrong?
their units. All right, let's look at their final units. Their final equation is loss. Is a foot, pounds. Oh, what the heck is a slug?
Yeah. It's just difficult to follow. Like, the equations I get are correct, but then when I get the final answer, it's wrong because I didn't multiply the both sides by g. If you use the original equation that
I think it's way easier to calculate in terms of head, right?
Yeah, that's what I initially did, but then it's the wrong.
But if you divide by g, would you get the correct answer?
No. Well, I mean, I guess you would in the units, but not in terms of the loss they noted.
Well, I'll just do the algebraic solution because I never ask for numbers.
Yeah, exactly.
I don't know what they're. Sometimes the solutions are incorrect, but I would just do it in terms of head. Like, I don't know why they want to do it in terms of. Why would anyone want to do it in terms of g times? So the units of loss is generally we have HL, and they're calculating GHL, and that is basically energy per density.
Because h sub l is just the height, right? The length.
Oh yeah, times area. All right, because basically mgh is energy, and so this is no, that's divided. It's divided by mass. Oh, it's energy per mass. That's what they're calculating.
Yeah.
Unless they asked for units of energy per mass, I would have just given the head.
The original equation.
Yeah, the head. Yeah. I guess they want units of energy per mass because how much additional energy is lost from section 2. And it all depends on flow rate. Because they don't even give you Q. They don't give you flow rate.
Yeah.
Oh, no, they give you Q. They give you V1.
Calculated V2 using unreached mass.
Yeah.
Okay, so that was my only question. Just the GHL was throwing me off.
Yeah.
Because we would just be expected to do actual head loss.
Is there a reason why it's being added instead of subtracted for the HL in that question?
Where do you see that?
Like plus the GHL rather than like subtracting what we usually do.
I think their sign's right. You mean the very first line?
Yeah.
They've got P out plus U out, U out plus G, C out is equal to P in minus HL. I think that part's okay.
Yeah, that's okay.
The out, basically the stuff coming out is always less than the stuff coming in. So I think that's okay. This energy, the energy equation can be a little awkward because of the unit. Because, the other problems we did in class, like, there are 3 ways to represent the answer. You can have energy per time, head. Okay, so there's the one version, which is head, which doesn't have the mass. And there's also just the power and watts. And then basically you have to do HL times G times M dot, I think, right?
Rho Q.
Yeah, rho Q, yeah. And they're kind of like doing something in between. I wouldn't worry about it.
And I just have one more comment.
When you're done, I drew out the picture for you.
Say that again, Daniel?
I said when you finish, I drew out a picture.
Oh, you did? Put in the chat.
In the chat?
Or send me the link in the chat. Or go ahead and share screens.
All right.
Go ahead.
Okay. 5.106